Have you ever wondered why planetary coordinates from different locations on Earth differ slightly? The cause of this unique phenomenon is diurnal parallax, which shifts nearby celestial bodies. Because of it, the Moon and Sun always appear slightly lower than their geocentric position. Astronomers utilize a specific equatorial radius of the planet to accurately standardize all reference data.
Welcome! In this explainer, we will conduct a detailed scientific analysis of diurnal parallax, a fundamental concept in positional astronomy. We're going to proceed systematically. First, we'll establish the observational problem. Then, we'll define the concept geometrically, quantify it, and finally, we'll discuss its practical implications in the field of astronomy. All right, let's dive in. The position of a celestial body is not absolute. It depends fundamentally on the observer's location. To really get this, we have to distinguish between two key viewpoints. The topocentric view is what we actually see. It's the view from our specific point on the Earth's surface. Then there's the geocentric view, which is a standardized, theoretical position as if we were observing from the exact center of the Earth. This gives us a common reference frame, independent of where you happen to be standing. Now you might be thinking, how big is this difference really? Well, for distant stars, it's so tiny it's practically imperceptible. But for the much closer bodies in our own solar system, like the Moon, the Sun, and the planets, this discrepancy becomes absolutely crucial. This is the very problem that the concept of parallax was developed to address. So let's move on and see how we can define this observational shift with some real geometric precision. Formally speaking, diurnal parallax is the angle, which we label P', that's created by those two different lines of sight we just talked about, the geocentric one and the topocentric one. To really visualize this, imagine a huge triangle in space. One vertex is at the center of the Earth. Let's call it O. Another is you, the observer, at point T on the surface. The third vertex is the celestial object itself, M. The parallax angle, P', is the angle at the vertex M of this cosmic triangle. And here's another really brilliant way to conceptualize this whole phenomenon. From the celestial body's point of view, the parallax angle is simply the apparent size of the Earth's radius. It's the angle that the line from the Earth's center to you on the surface would create in its sky. Now, a critical question comes up. Under what conditions is this parallax effect at its maximum? To figure this out, let's just consider the two extreme cases for where a celestial body could be in the sky. Okay, so first, imagine the object is directly overhead, at the zenith. In this case, you, the Earth's center, and the object are all lined up perfectly. Your geocentric and topocentric lines of sight are identical. The parallax angle, P', is 0. There's no effect. But now, picture that same object on the horizon. Here, your line of sight is perpendicular to the Earth's radius, and the angle between the two lines of sight is as large as it can possibly get. This is when parallax is at its peak. This specific maximum value is so important that it gets its own name, the horizontal parallax. We denote this one with a simple p, and it's a fundamental property for each celestial object at a given distance. So now that we have these concepts down, we can express the relationship between the general diurnal parallax and that maximum horizontal parallax mathematically. If we apply the law of sines to our OTM triangle, we get this precise relationship. It tells us that the sine of the parallax you observe, P', is equal to the sine of the maximum horizontal parallax P multiplied by the sine of zenith prime, which is the object's observed zenith distance. Now, here's where we can make things a lot simpler. For every object in our solar system, these parallax angles are tiny. I mean, for the Moon, it's about 57 arc minutes, and for the Sun, it's a mere 8.8 arc seconds. Well, in trigonometry, there's a handy property. For any very small angle expressed in radians, the sine of that angle is almost exactly equal to the angle itself. This is called the small angle approximation, and it allows for a major simplification. And here's the result. The formula becomes a very accurate, direct relationship. The parallax you see at any moment is just the maximum horizontal parallax multiplied by the sine of the zenith distance. It's an incredibly useful tool. So let's wrap this up by looking at the practical consequences of all this and why we need some standardization in astronomical work. This is probably the most important takeaway for any observer. Because of your position on the Earth's surface, a celestial body will always appear systematically lower on the horizon than its true geocentric position. And that maximum displacement is, you guessed it, equal to the horizontal parallax. But of course, there's a problem. The Earth isn't a perfect sphere. It's an oblate spheroid, which means its radius changes depending on your latitude. Since the Earth's radius is the baseline for our parallax triangle, this could mess up all our calculations. So how do we ensure consistency? Well, to resolve this, a standard is adopted. All official parallax calculations use the Earth's equatorial radius, defined as exactly 6,378 kilometers. This is our fixed baseline. The parallaxes that are calculated using this standard radius are called horizontal equatorial parallaxes, and we denote them with p(0). These are the universal canonical values you'll find published in astronomical almanacs. Now, what's really interesting here is just how vast the difference is between these standard values. You can see the moon's parallax is enormous compared to the sun's. This directly reflects the relative distances of these bodies from Earth. A larger parallax always means a closer object. And this chart just brilliantly illustrates the scale of that difference. The moon's parallax is nearly 400 times greater than the sun's. It's a striking visual confirmation of how much closer the moon is to us compared to our star. So we've seen how an object's position shifts just based on where you're standing on Earth. This leaves us with a final really big thought. If this small, earthbound shift is our first step, how could we use a much, much larger baseline, like the entire orbit of the Earth, to measure the even tinier, more subtle shifts of the distant stars?
Thank you, friends. Strive for understanding and become wiser. See you soon.